Hi everybody, I want to thank y'all for joining me today for this Cisco Live presentation. My name is Jay Vivas. I am a technical consulting engineer in the Cisco CX organization. I'm also a CCIE Wireless and the team lead for Cisco Wireless TAC at our RTP campus. Today we're going to take a look at using and troubleshooting central web authentication on the new 9800 series controllers. And quick note, in the presentation and in the logs, you'll see AuthC, which means authentication, and AuthZ, which is going to mean authorization. And as we discuss troubleshooting, I'll mention certain logs or packet captures that you would need to collect. If you're unsure about how to do this, just go to the appendix of this slide deck where I walk through how to do it. In the appendix, there's also config examples for the different types of deployments that you might have when using CWA. We're going to kick it off by talking about the CWA concept and what it is. Then I'll get into the packet flow and how it's expected to work. Once we know what to expect, we'll be able to spot when something unexpected happens. So I'm going to take you through each step and discuss what could go wrong and how to respond in these situations, what we need to collect in order to figure out where the problem is. I'll begin with some of the more generic problems that we'd see across any type of deployment, and then I'll move into some problems that are specific to local switching and some problems on ICE. So what is CWA? CWA is a layer 3 security that will present a web page to the client where they have to take some kind of action before they're allowed to use the network. It's important to mention that unlike a layer 2 security, CWA by itself doesn't add any encryption to the traffic over the air. You can use it in conjunction with the layer 2 security like PSK or .1x if you wanted to add encryption to the traffic, but since this is usually seen on guest and void networks, simplicity will probably take a higher priority than security. The page that gets presented to the client could be anything from an acceptance of user policy with legal disclaimers or an acceptance of terms and conditions where the user promises not to do anything illegal, or it can require a username and password that you give out to your guests and change frequently, or for even more security, it can be a sponsored page where the guest has to fill out some info and an email sent to someone in the company and they have to sponsor the user coming on the network. Now that we've discussed what it is, let's dig in and see how it works. So here's our topology. The first thing that's going to happen from the controller's point of view is the client will send an association request. The controller will take this association request and use it to create an authentication request or an access request and send it to ICE. ICE will then do a MAB lookup for the client, and we would have configured ICE to bypass the MAC address even if it's unknown, because in a guest network, you wouldn't know the MAC prior to the client trying to use the network. ICE will then send back an authentication response with an access accept along with the configured attribute value pairs or AVPs. At the very least, these AVPs have to include the redirect ACL and redirect URL. The controller will then apply these AVPs to the client and send the association response. The client will then have to go through the DHCP process unless it has a static address, which in a guest network we wouldn't expect. Once DHCP finishes, the client will need to open a browser and go to a page somewhere. This triggers a DNS request, which it should get a DNS response for. The client will then try to set up TCP with the address it received in the DNS response, and the controller will intercept this and set up TCP with the client. After the TCP setup, the client will send an HTTP GET, which the controller will also intercept and respond to with an HTTP OK, which has the redirect in it. This redirect URL will be for the CWA portal on ICE. The client will now send another DNS request for the redirect URL, which it should get a response for. This is to say that the DNS server they go to has to be able to resolve the redirect URL to the ICE IP address in order for CWA to work. The client will send another GET, this time for the portal page, and it'll log into the network, whatever that means for this deployment. ICE will then send back a success page and a COA or change of authorization to the controller. The controller will act the COA and trigger a MAC reauth event. The controller will then send another access request to ICE, and I should respond with another access accept, only this time the AVP should be the ones that we want applied to the client post-authentication. So here we see the radioactive logs from the 9800 controller. As we go through the flow that we just discussed, these are the logs we would expect to see when everything's successful. If there's a problem, we would need to go through the logs and find out where the flow stopped. For example, Just because you don't see the client IP learn successful log, you can't assume that the issue's with DHCP. Keep in mind, you also don't see the client added to the run state log. What we need to do is go through the logs and find the last successful phase, and then we can assume that the next phase is where the issue is. So keeping with our DHCP example, if we don't see the client IP learn successful log, but we do see the association response log, then yes, the problem is probably with the IP learn phase. Okay, so now that we know the flow, we can discuss how to troubleshoot the problems within it. What I'm going to do next is go through each of the steps we just discussed and talk about what can go wrong and the most commonly seen issues. The first thing you should see in the logs for the client is the association request. If you don't see this, then we need to go collect more data to find out why. We also need to keep in mind that this is the client's responsibility to send this packet, and we can't force them to do it. It's possible that the client just didn't send it. This doesn't always mean that it's the client's fault. There could be a legitimate reason for it. It's also possible that you're collecting logs on the wrong MAC address, not just because of a typo, which is obviously a possibility, but what we're seeing more of today, especially with smartphones, is they randomize their MAC when connecting to wireless networks. So you might be trying to capture logs based off the burnt-in MAC, but that's not the one that the client's using to associate to the network. This is a default setting on most phones, and you'd have to go into the settings to turn it off on that client. Or if the client at least gets to the phase where they have an IP address, then you can look up the IP address in the MAC that goes with it. Another reason why we might not see the association in the logs on the controller is that even though the client sends it to the AP and the AP sends it to the controller, it doesn't make it there. So how do we figure out what's going on? Well, with the client randomizing its MAC, that's just a setting on the client. You'd have to go look and see if it's doing it. For the other issues, we'd probably need to get an over-the-air capture or an OTA, and also some client traces from the APCLI and possibly a client dump from the APCLI. Whenever you take the OTA, I'd also take the client traces along with it just to get a better picture of what's going on. The client dump is pretty useful if you can't get an OTA, but it's not as robust. But for the situation that we're talking about here with the association request, it'd do the job. Now, when we get an OTA, if you see the probe request and probe response going back and forth to the client, then we can assume the MAC address is correct. Now, if the client receives the probe response but doesn't send the association request, then the issue is probably in the probe response. This doesn't mean the response is bad. It just means that the client received it and made a decision not to send the association request. At this point, I'd probably look at the probe request and probe response and make sure that one party didn't require something the other party couldn't provide. If the client does send the association request over the air but we don't see it in the logs, we need to check the client trace on the AP to see did the AP receive it and did the AP put it on the wire. If the logs say it did, then we need to chase the packet through the network, taking span captures or EPCs wherever available, and find where the packet dropped. After we've received the association request from the client, the controller should then send an authentication request to ICE. If this doesn't happen, then the problem is most likely in the config. We need to check and make sure that MAC filtering is enabled and there's a valid authorization method list on the WLAN. The authorization method list on the WLAN has to be tied to a server group that has a server in it. It's possible that the server group associated with the method list doesn't have any servers in it, or it did at one point and you removed it. If this is the case, then the message you see here is what will pop up in the logs. It's kind of misleading. It makes you think that we sent something to a server and it's not responding, so we marked it dead. But in all actuality, we just never had a server to send to begin with. Okay, so after we send ICE the authentication request, we would expect ICE to do the MAB lookup and send back the AVPs. If this doesn't happen, then we need to go into the live logs of ICE and see why. Here we can see two different problems. For the first problem, when we look at the authentication policy and the authorization profiles, there's nothing there. And that just means that whatever the issue is happened before those were assigned to this endpoint. So we go into the details page and we can see that the failure reason is the message authenticator radius attribute is invalid. And all that means is the shared secret doesn't match. When the shared secret doesn't match, ICE won't respond to the authenticator because it's an untrusted device. So in the logs from the controller, all you'll see is ICE timing out. Once we fix this, we went back through the process and now ICE is sending us an access reject. Again, we go to the live logs and we can see that the authentication policy is correct, but the authorization profile is a deny access. And the rule hit on the authorization policy is the default rule. So now we go back into the policy set and we look at the authorization policy and the rule that we expect it to hit, and we can see we're matching on two things, wireless MAB and that the called station ID starts with the SSID. We know that wireless MAB hit because that's also a condition on my authentication policy. But when we go into the details page for this endpoint, we can see that the called station ID actually ends with the SSID instead of starting with the SSID. Once this correction was made, we were able to get the expected results from this part of the process. So now ICE is sending back an access accept with some AVPs. And when we go into the logs, we can see the access accept and the AVPs that it sends back. In this instance, there's a VLAN 160, the redirect URL, and the redirect ACL. Now for this step to complete correctly, we have to be able to apply the AVPs that ICE sends back to the client. You see down below I posted some logs of some instances where we were unable to apply the AVPs that ICE gave us. The first example was the VLAN. On our controller, if the VLAN's not there, just like on a switch, if the VLAN's not in the VLAN database, we're unable to apply it to the client. The next example is the ACL was missing. So if ICE sends back an ACL name and there's a typo in the name or the ACL just hasn't been created yet, we can't apply it to the client and the association fails. The last example is AAA override being disabled, and this would be the same on any WLAN that expects to get AVPs back from a Radius server. If AAA override is disabled, we're unable to apply whatever the server sends back. The good thing about this is that the logs clearly state what the issue is. So if you grab the radioactive logs and you go to where there's a failure, you'll be able to see why it failed. On the last slide, we talked about when we received AVPs from ICE that we weren't able to apply. But it's also possible that the AVPs we receive from ICE are able to be applied, only they're the wrong one. So you won't receive a failure and the process will actually finish and move on to the association response. But when it's time for the client to use the network, whatever's actually applied to them could prevent them from doing that. In the CLI of the controller, if you do show wireless, client, MAC address, then their MAC address, and details, you can see these resultant policies in the output. In the GUI, you can go to the client details page and you'll see the same output. It's the same thing, it's just a different way of looking at it, whichever's easier for you. The point is that we check and make sure that what we expect it to be applied to the client is what's getting applied. So the output here, it was just to point out that the ACL that we received back from ICE is a punt ACL. This means that the ACL is going to decide what's punted to the CPU for further action, and in the case of CWA, that action would be a redirect. So deny will not punt it to the CPU, and a permit statement will. This is why we deny things going to ICE, but permit everything else. DNS and DHCP don't need to be on this ACL because they'll be allowed through by default. We only need to add that if we want to restrict what servers are used for these services. Also, we'll notice that the ACL is only applied in the in direction. This is to say that it's coming from the client and not going out to the client, which is why we don't have to put the return traffic in the ACL. You'll also see that there's two ACLs applied here. The second one is the implicit deny, but it's a security ACL, so deny in that case actually means deny. Once the AVPs are applied to the client, we'll send the association response. What we want to see here is response code 0, which means success. If the client doesn't continue on after the association response is given, we probably need to get an OTA to make sure it was actually sent over the air. And if it is, but the client's just not accepting it, we need to collect some logs from the client to find out why. So the next step is DHCP, or at least we're saying it's DHCP, because we expect that clients on a guest or void network won't have static addresses. It's actually the IP learned state. If the client had a static address and they were allowed, we would just need them to source some traffic with their IP address in the header, and they'd complete this state. But if it is DHCP, we need them to go through the DORA process. If DHCP fails, the first thing I do is test with a static address so I can see if there's a problem that's specific to DHCP or if there's a problem with all traffic. If the problem is with DHCP, we just need to follow where DORA stops like we would with any other DHCP issue and chase the packets through the network. Also, I want to mention that in these logs here, I only put the RX. You see they all start with RX, but in the actual logs, there will be a RX and TX for every message. So for the discover, did we receive it from the client, and then did we transmit it onto the network? In CWA, there are 2 times we can have DNS issues, before and after the redirect. Looking at the address bar in the client's browser would tell us which part we're at. If the redirect is there, then obviously they've already gotten the redirect. In the first screenshot, you can see I went to cisco.com because that's my home page, and I never got the redirect. An easy way to test DNS at this stage is to just put an IP address in the address bar instead of a domain name. Since we won't need a DNS server when we use an IP address, this bypasses it altogether. The IP address doesn't have to be valid or go to anything on the network. The controller will still intercept it and send the redirect. In the picture on the bottom, you see that I got the redirect, but I still can't find the page. And this is because DNS isn't working at all in this scenario, and we couldn't resolve the redirect URL either. After the first DNS request, the client will set up TCP and send an HTTP GET. The controller will then send an HTTP OK with the redirect. Here's a shot of the packet with the redirect and the HTML part. If the client doesn't receive this packet after TCP sets up, we would need to chase it through the network. From the client side, you don't need to do an OTA. You can capture directly on the client NIC, and on the controller side, you can just take an EPC. If the client doesn't send the GET or doesn't accept the redirect, we need to collect logs from the client to find out why. Okay, so here's the next time you could have a DNS issue. If it's a guest network, then it might be anchored outside of the network, and the DNS they use doesn't have the domain name for your ICE, so it can't resolve the redirect. Or maybe you got here because you put an IP address in the browser to skip the first DNS request. To test this in ICE, at the authorization profile, we can manually set the URL sent in the redirect. Here I set it to the IP address of ICE to, again, remove the need for a DNS server. This obviously isn't a permanent fix, as your guests wouldn't know to do this, and even if they did, once they got on the network, they don't have DNS connection. So I really only recommend doing this for testing or proof of concept. As you can see, when I use the IP address in the redirect, I am able to reach the ICE page, only there's a different kind of error. Which brings us to our next problem. Certificate errors. Now, there's a lot of confusion on this, so let me try to explain. Here we can see the two most common types of certificate errors. The first one on the left is saying that the certificate presented is a self-signed certificate. The one on the right is saying that the domain on the certificate doesn't match the domain the client is trying to reach. The reason for the first error is because it is a cert that the controller created and signed itself. You might ask, why would the controller present a cert if the page is on ICE? Well, here's where things get a little bit tricky. If the client starts the CWA process by going to an HTTPS page, after it gets the first DNS response, it sets up TCP with the controller because the controller is intercepting traffic at that point. Remember, we need the client to send an HTTP GET in order to provide the redirect. We're not that far yet. After setting up TCP, when using HTTPS, the client will need to set up TLS with the controller. At that point, a certificate has to be provided. And by default, the controller only has the self-signed certificate. So you might say, well, I'll just go get a trusted third-party cert and I won't see the issue anymore, right? Wrong. You will then most likely see the second error about the domain mismatch. This happens because you can only get a certificate for a domain you own. Let's say it's yourdomain.com. And if your client is trying to go to cisco.com, the domain on your cert will not match the domain the client is trying to go to. The only way you would not get this error is if the client's homepage or the domain they're trying to go to is your domain, which on a guest network is highly unlikely. This is the whole point of HTTPS. It was created to encrypt traffic and ensure the client that the site that they are on is the site they expect to be on. However, with CWA, when we intercept the traffic, we are essentially a man in the middle, and we do not own the domain where they are expecting to go. So you might say, okay, there's no need for a cert on the 9800 then, right? Well, that depends. I've seen on some browsers, on some versions, they will not accept the self-signed certificate prior to the redirect. It won't even let you bypass it. Whereas if you presented a trusted third-party cert, it would. Now, you can see these errors both before and after the redirect, but the problems discussed here only apply to before the redirect. This is because once we supply the redirect, you would own the rights to that domain because it's the domain we gave them in the redirect. The good news is most operating systems will see that this is a captive network and open a browser for the client and send them to an HTTP page. Even most browsers will do the same. They'll tell you that you need to log in, and you click login, and they'll open up a new tab going to an HTTP page. The reason this is okay is because the first page you go to doesn't matter at all. It doesn't need to be secure. The only reason we need you to go to that page is so we can provide you with the redirect. Once the client has the redirect, the page they're going to then is HTTPS. So anything the client sends to ICE will be encrypted. So to sum it up, prior to the redirect, if the client starts with HTTPS, you cannot avoid the certificate errors. But After the redirect, all errors can be avoided with the presence of a certificate signed by a trusted CA. All right, so now that the client has gotten to the redirect, they'll have to sign in through whatever process you've set up on ICE. If there's any problem with the sign-in process on ICE, you'd have to go through the live logs on ICE and troubleshoot from there. The next point where the wireless infrastructure comes into play would be on the COA. You can see here the logs we would see once we receive the COA and start the MAB reauth. The controller would then send off another access request, and ICE should send back an access accept with the post-auth AVPs. If you don't see the COA in the logs, first thing to check is to make sure that ICE is sending the COA on port 1700 because that's the port that the controller will accept. If it is, we would take a TCP dump on ICE and an EPC on the 9800. If it was sent but not received, again, we need to chase the packet through the network. Okay, so we're done with all the generic problems. We're going to move on to some issues that are specific to a locally switched environment. The main problem that we see with CWA and locally switched networks are issues with the ACL. Because of that, we don't download every ACL to every AP that's in Flex Connect mode. If we did this, we'd run out of memory depending on how many you had, or we'd have to cap how many you could create. Instead of doing that, we allow you to decide which ACLs will be stored locally by which APs. You do this in the Policy tab under the Flex profile. Also want to mention whenever you add the ACL to the Flex profile, you got to hit that CWA checkbox there. This is because the APs don't share the same concept of punt ACLs, so we need to flip the deny statements to permit statements and vice versa. So whenever you hit that box before it's sent to the AP, that's what's done. Alternatively, if the ACL is only going to be used in Flex locally switched environments, then you could just create a normal ACL and not check that box. Another thing that we need to talk about with ACLs in a Flex Connect locally switched environment is the ACLs are applied in both directions. In a centrally switched environment, that's not so. It's only applied on the in direction. So this means that if the ACL is going to be used in a Flex locally switched environment, you would have to deny traffic going to ICE and also deny traffic coming back from ICE. Another situation that you could get into is that the ACLs are just missing from the AP. When you go to the CLI and run the command show IP access list, you don't see it there. If you run into the situation, just change the Flex profile to something different and then change it back, and that should trigger it to download the ACLs again. The last ACL issue I want to bring up for Flex local switching is the VLAN ACLs. VLAN ACLs are always applied to the VLAN no matter what. So if you have a client on a VLAN that has a VLAN ACL, even though there's a redirect ACL that's added to the client, the VLAN ACL is also added to the client. You can do this if you want, but you'd have to allow traffic to ICE in the VLAN ACL as well. I would say the best way to get around this is to not use a VLAN ACL in these situations and just send whatever ACL you want to be added to the client post-auth in the post-auth AVPs. The last Flex Connect problem we're going to discuss is the VLAN not being on the AP. Just like a switch or the controller, the VLAN has to be in the VLAN database. The AP has to have the VLAN created. So if ICE sends back a VLAN in the AVPs that's not on the AP, you'll get that delete reason, exclude VLAN fail. So there's two ways you can get the VLAN on the AP. One, if it's already mapped to a WLAN, then the AP will create it. And the other way is to go into the Flex Connect profile and add it under the VLAN tab. This is the same place where you would add a VLAN ACL, only this time you just leave the ACL part blank. The last thing we're going to talk about are some common issues that we see on ICE that can sabotage the CWA deployments. Just because the client completes the portal page doesn't mean that Webauth is over. If your client goes through the whole process and the controller keeps it in Webauth pending, you need to collect the radioactive logs from the 9800 and look at the failures. In the logs, go down to where you see the COA and then start from there. In this instance, we can see that the client started the process on one VLAN, and then after the COA, the post-auth changed it to a different VLAN. This is not allowed, and you can clearly see this in the log. Here we can see that even after the COA, ICE is still sending back redirects. When we look at the client in the live log, we can see that there is a time where the identity is the MAC address and another time where the identity is the username. This tells us that the client is definitely going through the CWA flow and logging in, or else ICE wouldn't know the username it was using. We can see that even after the login, it's still getting the same authorization policy. We go and look at the policy set, and we can see that guest flow condition is there, only it's below the MAB condition. The rules in a policy set read the same as an ACL does. It starts at the top and goes down until it hits a rule. Once it hits a rule, it stops and applies the rule it hit. So to resolve this issue, we just need to switch the order of those two rules. the post CWA rule should be on top. When the client first comes in, it won't hit that rule because it hasn't gone through guest flow yet. So it'll bypass that rule and go down to the MAB rule, which it will hit, and then the next time it comes around, it'll hit guest flow and not get the redirect. A bit earlier in this presentation, we talked about the client not moving on from the IP learn state after the association response. Remember, I told you this is something that the client has to decide to do. One of the common reasons we see that the client might refuse to move on is because they timed us out on the association response. Clients have timers just like the infrastructure devices do. I've seen clients have timers as small as 200 milliseconds and as large as 350 milliseconds when talking about the association response. If you look at the timestamps of these three messages here, you'll see that there's over 500 milliseconds between the association request and the association response. Surely, we've missed the timer on this client even though we didn't miss the radius timeout on the controller. When this happens, it's expected that the client will not move forward. They might even blacklist the WLAN for a short time. To investigate where the issue is, we need to have time-synced packet captures on the switch ports connected to the AP, the controller, and ICE. Then we can match up when the packet leaves one device and arrives at the next device, and then leaves that device and goes to the next device. Looking at those timestamps, we should be able to tell where the latency is. Well, team, that brings us to the end of this presentation. I hope you were able to pick up some helpful tips, and I would encourage you again to go through the appendix, check out the data collection section, and the config examples. I want to thank you all for joining me today. I wish you the best of luck in all your networking adventures.